Hi everyone, I'm Tushar Nagarajan and this is our work on learning a structured representation for egocentric video. Third-person video understanding typically involves answering where and what questions about intentionally captured video of salient moments. In contrast, in egocentric video, we see the world through the eyes of the camera wearer. The video captured is strongly influenced by how the camera wearer interacts with the world around them, leading to more interesting questions like what will the camera wearer do next? What areas in the environment are important for this activity, or how should a space be used to complete this activity? The real stars of ego video are both the camera wearer and the environment. Despite this link, current video models treat video as fixed-sized chunks of frames and completely ignore the underlying persistent environment. On the other hand, dense reconstruction methods build elaborate 3D point cloud models of spaces, but don't factor in how these are relevant to human interactions and preferences, and commonly fail due to quick camera movements in typical ego videos. Our idea is to build a topological graph of the environment that captures how people use it. We reorganize ego video frames into a set of activity zones and the rough spatial layout. Each zone represents a location in the environment where a coherent set of interactions can be done. The zone catalogs all the times the camera wearer visits it and all the interactions he performs there. Our grounded video representation allows us to better reason about the agent who may take a commonly traversed path to the sink after picking something up at the fridge, or to reason about environment affordances to plan out what interactions are possible at what zones. To construct this graph, we first train a localization network to classify if two frames belong to the same zone or not. Apart from visual and geometric cues, we leverage cues from human behavior. Contiguous frames during the course of an interaction, temporally adjacent frames, and frames of functionally similar locations are matched, despite visual differences, to train a robust similarity network. Once trained, the network is used to sequentially assign a similarity score for each frame of an egocentric video, with each node of the graph. If these scores are low, the frame represents a visit to a new unseen zone, and if it's high, then the frame is merged with the previously visited node. Over time, a graph is constructed frame by frame for each egocentric video to capture zones of human interaction, and visits to each of these zones are catalogued. We'll now see two important tasks that we use our EGO-TOPO graphs for: anticipation and scene affordances. In our long-term anticipation experiments, the model must watch a fraction of a video and then predict the set of future actions in the remaining video. Unlike traditional anticipation, which focuses on predicting the action in the next 1 second, this task requires an understanding of how much of an activity has elapsed and what's required to complete it, for which a reliable encoding of past video is essential. To do this, we first encode the video as a topological graph and aggregate all visits to nodes as a feature vector. We then encode the graph using a graph convolutional neural network to generate a video feature for classification. Our model has the advantage of factoring past information in nearby locations to inform future prediction. Our method outperforms other pure video aggregation schemes that don't consider the structure of the underlying environment. For our experiments on environment affordances, we ask the question, what all interactions can I do here? The clip that this frame was taken from gives us only a partial picture of the possible interactions. In reality, there are many other likely interactions, many of which have not been seen performed in exactly this location. To discover these, we first find the node in our topological graph that the frame corresponds to. We link zones across environments that have similar action and object distributions, implying similar functionality. This consolidated zone across environments captures the variety of interactions possible and paints a more complete picture of the frame's affordances. We use this to propagate labels between frames to train an affordance model. Using our topological graph and cross-environment linking offers large improvements over methods that consider label propagation via physical proximity like SLAM or visual similarity in a k-means clustering of frames. Here we show a graph for an egocentric video, and results of our affordance model apply to each node in the graph. In conclusion, egocentric video is much more than just a stack of frames. Treating frames of the video as visits to nodes in a topological graph puts the agent and the environment's relationship at the forefront and allows us to effectively reason about the two.